In this lesson, we will focus on the techno-economic analysis and future trends within Project 3, composite machining technology, and advanced manufacturing case studies from the course Metal Cutting and Tooling. We will dive into the economic considerations of composite machining technology, learning how to conduct a scientific economic analysis. Additionally, we will explore the future development trajectory of this technology through practical case studies, such as applications in national strategic industries like aerospace engines and micro-electromechanical systems. Students will gain a more intuitive understanding of the importance of composite machining technology, inspiring a sense of mission to serve the major strategic needs of the nation. In the field of metal cutting, composite machining technology is an advanced manufacturing technique that integrates multiple machining methods into one. It allows for the completion of various machining processes on a single piece of equipment, significantly enhancing both efficiency and precision. Next, we will explore this in detail from the perspectives of techno-economic analysis and future trends. Techno-economic analysis primarily involves evaluating the cost-effectiveness of composite machining technology in practical applications, essentially considering the relationship between input and output. When conducting this analysis, we need to take multiple factors into account comprehensively. 1. Equipment cost. Composite machining equipment is typically expensive, representing a significant portion of the initial investment. For instance, the price of an advanced composite machining center can be several times that of a standard machine tool. Equipment costs include the purchase price, transportation, and installation fees. Tooling cost. Composite machining may require the use of various types of tools, and the costs associated with purchasing, sharpening, and replacing these tools can add up. Additionally, some high-precision tools can be quite expensive. 3. Labor cost. Although composite machining technology can reduce the number of processes and operators required, it demands a higher skill level from operators. This necessitates specialized training, which can increase labor costs. 4. Maintenance costs. Composite machining equipment has a complex structure and high maintenance requirements. Maintenance costs include expenses for regular servicing and parts replacement. 1. Increased production efficiency. Composite machining technology can complete multiple processes in a single setup, reducing the number of times a workpiece needs to be clamped and the adjustment time for the machine tool, thereby significantly enhancing production efficiency. For example, when machining complex components of aerospace engines using composite machining technology can reduce the processing time from several days to just a few hours. 2. Improved machining precision. By reducing the number of clamping operations, composite machining minimizes errors associated with multiple clamping, thereby enhancing the machining precision and surface quality of workpieces. This is particularly significant for parts with extremely high precision requirements, such as the tiny components in micro-electromechanical systems. 3. Stable product quality. A stable machining process and high precision results lead to more consistent product quality, reducing the defect rate, and increasing the product's pass rate and market competitiveness. To evaluate techno-economic efficiency more intuitively, we can use certain economic indicators, such as the payback period T. The payback period refers to the time required to recover the initial investment through the net earnings of the project. The formula is T equals 1 divided by where I represents the total initial investment, including equipment costs, tooling costs, and other upfront expenditures. A represents the annual net earnings, which is the annual sales revenue minus the annual operating costs, including labor costs, maintenance costs, etc. For example, if a company invests 5 million yuan to purchase a composite machining equipment and expects an annual net earnings of 1 million yuan, then the payback period T equals 500 over 100 equals 5 years. The shorter the payback period, the better the economic viability of the project. Aerospace engine manufacturing. Aerospace engines are the heart of an aircraft, and their manufacturing technology represents the pinnacle of a nation's manufacturing capabilities. The components of aerospace engines are complex in shape and require high precision, making it difficult for traditional machining methods to meet their manufacturing demands. Composite machining technology plays a crucial role in the manufacturing of aerospace engines. For example, the blades of an aerospace engine have complex curved surfaces that require multiple machining processes, such as milling and grinding. By using composite machining technology, roughing, semi-finishing, and finishing of the blades can be completed on a single piece of equipment, significantly enhancing machining efficiency and precision. Additionally, by reducing the number of clamping operations, the machining quality of the blades becomes more stable, thereby improving the engine's performance and reliability. Micro-electro-mechanical systems, MEMS, are miniature devices or systems that integrate various functions, such as microsensors, actuators, signal processing, and control circuits. The size of MEMS devices typically ranges from micrometers to millimeters, requiring extremely high machining precision and surface quality. Composite machining technology can integrate various processing methods such as photolithography, etching, and micromilling to achieve efficient and high-precision manufacturing of MEMS devices. For example, in the manufacturing of MEMS accelerometers, composite machining technology can precisely fabricate microstructures on silicon substrates while ensuring their electrical and mechanical performance. This integration of multiple technologies makes the manufacturing of MEMS devices more efficient and reliable. Intelligent development. The future of composite machining technology will evolve towards intelligence. By incorporating technologies such as artificial intelligence and big data, it will enable automatic monitoring, optimization, and decision-making in the machining process. For instance, sensors can be used to monitor parameters like cutting force and temperature in real time during the machining process. Through data analysis and machine learning algorithms, machining parameters can be automatically adjusted to enhance machining quality and efficiency. Green development. With the growing awareness of environmental protection, composite machining technology will increasingly focus on green development. This includes the use of eco-friendly cutting fluids, optimizing machining processes to reduce energy consumption, and improving material utilization. For example, green measures include dry cutting, minimum quantity lubrication, MQL, low temperature, liquid nitrogen cooling, biodegradable cutting fluids, and real-time energy efficiency monitoring. These measures reduce environmental pollution while also lowering production costs. Deep integration of multiple technologies. Future composite machining technology will not merely be a simple combination of several machining methods, but rather a deep integration of multiple technologies. For instance, future applications may include energy field coupling processes such as laser ultrasonic milling, synchronous loading, and ultrasonic assisted laser cladding in composite machining. This will achieve the integration of multi-field coordinated material removal and surface modification. Composite machining technology has significant applications in national strategic industries such as aerospace, defense, and new energy. Mastering the system integration capabilities of composite machining technology is crucial for China in building a strong manufacturing nation. As students in the relevant field, we must recognize the mission we bear, strive to learn and master composite machining technology, and contribute our efforts to the technological development of the nation. In this lesson, we conducted an in-depth discussion on the techno-economic analysis and the future trends of composite machining technology within the course Metal Cutting and Tools. In terms of techno-economic analysis, we learned that cost factors include equipment costs, tool costs, labor costs, and maintenance costs, while benefit factors encompass increased production efficiency, improved machining precision, and stable product quality. We also studied the method for calculating the payback period. Through advanced manufacturing cases, such as aerospace engines and micro-electromechanical systems, MEMS, we observed the important applications of composite machining technology in national strategic industries. In terms of future trends, composite machining technology will develop towards intelligence, green development, and deep integration of multiple technologies. We must recognize the critical significance of mastering this technology in serving national strategic needs and building a strong manufacturing nation. I hope everyone will further reflect on these topics after class to deepen their understanding of composite machining technology.